Good morning.
Good morning. All right. So got through the first marking period. Everybody did overall, most people did very well on the first test, which is very good. You guys are doing well. Just keep up the good work. And move into part 2 of this course. And today is chapter 7. So I should get right into it. And I do have an example problem, actually set of problems that are in the back of the chapter that illustrate the things that I'll be going over today. So I'll be going over that also. So if you have your calculator with you, that would be good. Make sure that's near you. I don't have any display of that calculator. Unfortunately, they don't seem to have the HP. I don't think has that for this calculator. So I'll do my best to explain using the calculator. But I think most people know how to use a scientific calculator. But okay. So I got
No,
you.
I don't.
But if you don't, I'll try to explain the steps with you. Right? All right. So Luna, I got your message. That's okay. Um, all right. So let's get to it, and we'll get to the PowerPoint. And so this particular there we go. This particular chapter is called Summarizing and Displaying Measurement Data. All right. So let's start with the first thought question. It says here, if you were to read the results of a study showing the daily use of a certain exercise machine resulted in an average 10-pound weight loss, what more would you want to know about the numbers in addition to the average? And the hint at the bottom says, do you think everyone who used the machine lost exactly 10 pounds? So when we average, come up with 10 pounds, what other information would you think we would need?
I think that you would need all of the numbers of each person that did it because it's not saying that each person lost 10 pounds. It says an average. So that can literally be a whole range of numbers.
Right, the range of numbers. Right, right. Now, there could be, 100 or 200 people in this study. So one thing we want to do besides the average, which is sort of we could say it's a number in the middle, right? Something like in the middle of all the numbers. You mentioned about the differences in the weight losses for each of the people. So the way we would describe it is we need some measure that measures what's called the variability, how variable the numbers are from each other in the data set. All right, so we don't have to know each individual value. Of course, we would if we were going to calculate these numbers. But as far as, let's say, if we were describing this to somebody, the study, we would give them the average, and then should give them some idea of how variable the numbers in the data set are. Okay, so that's a very good point. Anything else? Okay. So suppose you're comparing two job offers, and one of your considerations is the cost of living in each area. You get the local newspapers and record the price of 50 advertised apartments for each community. What summary measures of the rent values for each community would you need in order to make a useful comparison? Anybody?
Would you get the average of each?
Yes, average is good. Also, we could talk about the variability too, but I think they're giving you a hint about additional information. What else would you want to know? Well, they give you a hint in the bottom here because they said, would lowest rent in the list be enough information? Well, the lowest rent would be good to know. How about the highest rent, right? How about the one in the middle? We would call that the median. Maybe the median rent would be good to know. In addition to the average, in addition to how variable they are. Okay, all those things would be useful. There's another one. The real estate website reported that the median, here we go, the word median, the median price of a single family homes sold in the past 9 months in the local area was 136,900, and the average price was 161,447. How do you think these values are computed? So let's look at the average first. How would you calculate the average? So we have 9 months of data, right? How would you come up with the average? Nobody?
To compare the family homes, like all the family homes.
No, I'm actually asking, how would you compute it? How would you compute the average? If you were given all 9 prices, all right, and all 9,
Wouldn't you
Would you
just
add
add
it?
all,
Would you
add
add
them
all
all and
of
then
it?
divide them?
add
by
them
two.
all,
Add all of it?
and then do what?
Divide them by however many numbers are there.
And how many
Basically
numbers
finding
are
the
there in
mean.
this case? How many numbers are there?
9.
9.
Oh, yeah.
Yeah. So you add up
So-
all 9 prices and divide by 9. That's the average. How do you find the median?
It's the number in the middle, isn't it?
Yeah, yeah. And when you say middle, you have to order the
From
prices
from
from smallest
great-
to largest. I'm sorry, is that what you were going to say? I think somebody was.
Yes, I said from least to greatest.
That's right. That's right. So you order the numbers from smallest to largest, and then find the one in the middle. Now, the one in the middle, how would you find the one in the middle? Well, if there's 9 of them, then it's the 5th one, right? That's the one in the middle. There's a little, just for you to know, there's a little short computation you can do to find which position in the middle. Let's say you had 105 numbers to find the median, all right, 105 of them. How would you find the middle one? Well, if there's 105, you would add 1 to 105 and then divide it by 2. So you add 1 to the number of numbers in your data set and divide by 2. Now, when you do that, if you have an odd number of numbers in your data set, like 9, when you do that, you'll come up with an even number when you divide by 2. So 9 plus 1 divided by 2 is 5. And that's the 5th number in the data set that's ordered from smallest to largest. The 5th number is going to be your median. What if you had an even number of numbers in your data set? Let's say you had 10 numbers in your data set. Well, 10 plus 1 divided by 2 is 11 divided by 2, which is 5.5. That's telling you that the 5th and the 6th numbers in the data set should be averaged, right? So the 2 middle ones are averaged. So if you have an even number of numbers in your data set, you find the 2 in the middle and you average them. If you have an odd number of numbers in your data set, it's just the one in the middle, right? That's typically how you find the median. Some of you probably already know that. All right, here's another question here. It says the Stanford-Binet IQ test is designed to have a mean or average for the entire population of 100, right? All right, and it is also set to have a standard deviation of 16. Now, standard deviation, we'll find out, is a measure of variability. It's an average, it's basically how, on average, how far apart are the data points, or the data values. So in this case, it's 16. So the average is 100, the standard deviation 16. What aspect of the population of IQ scores do you think is described by the standard deviation? And I just described it, it's the variability. Does it describe something about the average? Right. So does the standard deviation say something about the average? Well, what it does, it's taking the average of each data point's distance from the average. That's what the standard deviation does. It's the average distance from the data point to the mean. So it does use the average or mean, but it does it in the computation. But it's doesn't mean it's not the mean average itself. It's the measure of variability, right? So don't worry about that so much if that's a little confusing to you. They do have formulas for it, and we'll talk about that in a minute. So don't worry about that. And then the next one, students in a statistics class at a large state university were given a survey in which one question was asked was their age. All right, so they were asked, how old are you in years? One student was a retired person, and her age was much larger, obviously, than the others, and it's called an outlier. Right? So an outlier. So what is an outlier? Can somebody just describe it to me again? An outlier would be.
It would be like one number that doesn't fit in with the rest.
That's it. It's either too small or too large. Yeah. Now, there are ways of calculating an outlier, because one person might say a particular number is an outlier. Another person would say, I don't think it's an outlier. There could be some dispute about that. So there is a computation. We're going to learn what that computation is in a little bit. All right. And that determines whether there's an outlier and what the outlier is. It says if the students' heights were measured, would the same retired person necessarily have a value that was an outlier? So in this case, it's heights. Do you think the retired person would necessarily be an outlier in that case? Well, their age would be, right? I mean, I'm an example of this, by the way, with age, because when I
were measured
about 10 years ago, I started taking math classes. I wanted to teach math, so I didn't have enough credits. I had to take like 30 credits of math in a year. And when I was in the class, I was taking it at Rowan, some of these classes, and every student in the class but me was in their 20s. And I was, I believe at that time, I was like 57 or 58 years old. So I was definitely an outlier in terms of age, but do you think I was an outlier in terms of height? Maybe, maybe not, right? I'm on the short side, but certainly there are other students who were shorter than me. So not necessarily an outlier in terms of height. All right, now in terms of data, these are the 4 types of things that we look for when we look at a data set. We look at the center of the data set, which is either the mean or the median. We look for unusual values, small or large. Now, one of the reasons we do look at unusual values is because it's possible that whoever recorded the values could have made a mistake. Sometimes that happens. So we always check for unusual values to make sure they weren't mistakes. Number 3, variability. We talked about that. And number 4, the shape of the distribution, and we'll talk about that in a minute. So here's a data set. All right, these are 28 exam scores. All right, and actually, this particular problem that you see here is the one that we're going to be doing. I think this is the same one. Yeah, that we're going to be doing in the back of the book. So they're going to show you some things here. Let me just make sure.
Professor, can I ask a question? Are we going to be doing a lot of calculations?
There'll be some. It is statistics, but it's not as much as a Stat 1 course. All right, that's the difference. This one is a little lighter on calculations, but we can't get away from them. It's a math and stat course. There's going to be some calculations. So far, so good, right? These calculations aren't hard. And many of the ones that we'll be doing later will be using software and things like that. So mostly an interpretation class, but you will have to do some calculations. Now, here are 28 exam scores. And when you added them all up and divided by 28, you get this as the average. The median, well, you'd have to, now, what they did in this case here is they actually ordered everything from smallest to largest for you, but as you'll see in the back of the chapter, they'll have the same question as this. They don't order it, so you have to order it. All right, you have to start, and unfortunately with the tools that you have, now one thing you could use if you wanted to in this course is Microsoft Excel. If you're familiar with Microsoft Excel, the spreadsheet program, you can order. There's different things that you could do to a list of data in Excel. One of the things you could do is sort the data. So that's something that you can do. So if you're familiar with Microsoft Excel, you can use it. But if you had to do it by hand, it takes a little while, but you can do it. So you have the mean. The median is the number halfway in between, halfway from the smallest to the largest, but there's an even number of numbers in the data set, 28. So you have to find the two middle values and average them. Now the question is, where are those two middle values here? Well, like I said before, you do a little calculation. You take your 28, the number of numbers in your data set, you add 1, which makes it 29, and divide that by 2. That's 14.5. And that means you average the 14th and the 15th numbers in the data set. So you just start from the beginning. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the 14th number is 78. And the 15th number right over here is 79. You average those two, you get 78.5. That's how they came up with that. All right, so it's not that hard. The mode is the most common value in the data set. Okay, and you have to have it's the most frequent common value. It's the most common value, most frequent one. Now, there's no mode in this case here because no single mode, because there are many that occur twice. So if I was going to list the mode, I would list all of them that occurred twice. So for example, 64, 75, 78, 79, 80 are modes, all right, because they occur twice. Now, if you have a data set and there's no repeats of any numbers in the data set, then there's no mode. You would say no mode, all right? But if there's a tie, you would list all the ones that are most frequent. There's none in here that occur 3 times. There's a few that occur twice. So you would list all those and that would be the mode. All right, outliers. Well, it's possible 32 is an outlier because it's much smaller than everything else. We don't know about any of these others, but 32 is the potential outlier for sure. Maybe 55, but 32 for sure is a potential outlier. How would we figure it out for sure? Again, there's a calculation we'll go through. Variability, how spread out are the values? All right. So that's one of the things we have to figure out, is a measure of variability. Now, one measure we could take is the range. I don't know if they mention it in here, but the range is a very simple calculation. You just take your maximum number and subtract the smallest number. So the maximum number is 98, the smallest number is 32, and you subtract them and you get 66. That is called the range. Now, it's not a very, it's a measure of variability, but it doesn't tell you about the variability between 98 and 32. All right, doesn't say anything about that. So it's an okay measure of variability, but it's not fantastic. It's better if you can use all the numbers in the data set to calculate variability. And again, I'll show you that in 2 minutes. All right, and again, oh, here it is right here, the range. All right, so again, it's easy. Maximum number minus minimum number. Even the word range sounds like that, so it should mean that, right? It means maximum minus minimum, 66 points. They measure 2 other measures of range. One is called the interquartile range, which we will discuss in a minute, and the other is called the standard deviation. Now, the shape of the distribution has to do with where are the data values? Are they all clumped in the middle with values tailing off both to the left and to the right? Or do we tail off to the left, or do we tail off to the right? All right, so that's called the shape of the distribution. Now, one way we can look at how we can show pictures of your data, one of them is called a stem plot, and the other one is called a histogram. Now, this is for numeric data, all right, numerical data. Now, I'm going to show you, now, the histogram, which is on the right there, I'm going to show you another way of doing it in a minute. But the stem plot on the left is typically done in this way. If you let's say your numbers in your data set are all two-digit numbers. Now, you know the first digit is the tens digit, right? Because you know, like 32, the 3 represents the 30s, right? That's the tens digit. And then the next digit next to it is the ones digit. All right, so 32 is the number in the data set. So what you do is you create a vertical line, and then to the left of that line, in this case, you list all of your tens digits in the data set. So they happen to run from 3 to 9. Now, every data set's different, so you have to sort of take a look and see how you would construct it. And then on the right, the digits here are the ones digits. So for example, 3 and the 2 represents 32. The 5 and the 5 represents 55. Now, what do you do if you have more than one number in the tens digits? Like in the 60s here, we have several. We just put them, we list them to the right of the 6, for example, here, to the right of the vertical line. So 6 and 0 means 60, 6 and 2 means 62, 6 and 4, 64. There's 2 64s, 61, 68. Now I tend to put them in numerical order here. There's a value of doing that. I'll show you when I actually show you this problem the way I did it. I want to show it to you so that it'll become clear why you want these in numerical order. And here are the 70s. There are 1, 2, 3, 4, 5, 6. There's 8 numbers in the 70s. 75, 76. Here's another 75, 79, 78, like that. So that's how you read this. The first digit to the left of the vertical line is the tens digit, and then you have your singles. Single digit numbers here to the right, right? And they even have a little key here that tells you how to read it. Any questions about the stem plot? It's pretty easy. And they tend to call this also a stem and leaf plot because on the left they call them the stems and on the right they call them the leaves, all right? Because it creates sort of like a tree type shape. Now, the advantage of the stem plot is that you can plot it. You can see the sort of the shape of the distribution if you drew sort of a curve around all the numbers. And but you can see all the numbers. You can see every number in the data set, right? And that's one of the big advantages of that. And typically when I test you, both on this next test and on the final exam, I like to give a stem plot because I want to make sure that you understand what a stem plot is, that it's really a way of displaying all the numbers in the data set, and that you can read any number in the data set from the stem plot. You can see them. Now, another way of displaying numeric data is called a histogram. Okay. And what they're showing to the right here is an example of a histogram. A histogram typically is running along the x-axis is the numerical variable with different values. Okay, here's 45,000 all the way up to 81,000. And then running along the y-axis is what's called the frequency, and that just means count. So what you're basically doing is counting the number of values that are that are for these particular values down on the bottom here. How many are there that are 45,000? How many are there that are 49,000? Like that. Now, I will show you an example using these exam scores, how to create a histogram and how to read it. All right, but we'll do that at the end of today's session. I'll show you that example. All right. Now, what's the advantage of a histogram? You can really see the shape of the distribution if you create it. If you have you do a curve around this like that, you can see that it's pretty symmetric. Not perfectly symmetric, but it looks pretty symmetric. Right. So you can see the distribution pretty well. You could see the mode. right? The mode is up here, right? You can see the mode, it's the highest frequency one, like that. So you can tell quite a bit about this about the data set by looking at a histogram. And it tells you how to create a stem plot here. Now, you're not going to be creating these on this course. You're going to be interpreting it and also being able to read a stem plot, but it tells you how to create it. All right. And there's a couple different ways of creating one. You can have stems where you can repeat the same tens digit. For example, you can have 5 and 5, where the first 5 would have all the singles digits that run from 0 through 4, and then the second one would be all the singles digits that would run from 5 to 9. All right, so you could do it that way. Again, I will show you the example when I get to it. All right, here's another example here. Now, in this example here, what you're plotting on the stem plot is a large number here. These are incomes that have 5 digits to them. Okay, 5 digits to them. And what they're doing here is they're basically, this is a little confusing if you're not used to this. They're plotting on the left here the 10,000th digit, this first digit, and then the leaves are the thousandths digit, and they're just saying, all right, it doesn't matter about these 3 digits here. Any numbers that have 46,000 would be listed as 46 over here. So it's a little confusing if you're not used to seeing something like this. I would never give you an example like this, by the way, as far as a stem plot. And then he's showing you other examples here. In terms of shape of the distribution, you could see that this one here looks like it's it seems like most of the numbers are in the 60s. Here, most of the numbers are bigger than the 60s. Here, it looks like most of the numbers are smaller than the 60s. All right, so you have different types of shapes here. This looks like like a bell shape. This one is most of the data is to the right, and it's sort of tailing to the left. This one here, most of the data is to the left, and it's tailing to the right. When I say left and right, you have to sort of picture this, the stem plots sort of rotated, and where the 4, 5, and 6, 7 would be on the bottom instead of running along the vertical here. All right, and they show you how to create a histogram. I'm going to show you in a minute how to do that. And again, I'm not going to ask you to create these graphs. I'm going to show you these graphs, and you're going to be able to interpret them. That's the whole idea. Here's an example. Now, here's a histogram where the variable is running along the x-axis and the frequency is running along the y-axis. And this one, it's reverse. This could be confusing to people, right? Where the count is running along the x-axis and the variable is running along the y-axis. So they have it looking like this one, in this way. So a little confusing, but if you're used to looking at charts like this, not that hard to determine. All right. This looks pretty, again, if you flipped it a little bit, you would be able to see this looks kind of symmetric. And this one looks like it has 2 peaks to it. There's a peak right here, and there's another peak over here. All right. So that's sort of what they're trying to show you there. Here's a case where most of the data is to the left and it's tailing to the right. Okay. How do we know it's most of the data? Because the frequencies, the counts. All right, most of the counts are over here. The heights are the counts. So the data exercise is small values to the left, and then it sort of tails off not many large values to the right. Right. And you can picture if you ran a curve around this, it would be peaked over here, and then it would run down and then tail off to the right. All right, so let's talk about the language here. When you draw a histogram, let's just talk about the histogram. If you draw a histogram, and the data sort of looks like it's symmetric, that means if you drew a vertical line down the middle, the left side and the right side will look approximately the same. And an example would be bell-shaped curve, and that's called symmetric. Another term, unimodal, that means if you draw a histogram, you would see one place where there was the largest height, and that would be called unimodal. Bimodal would, you might see two places where you have peaks or heights, the rectangles. Now, skewed to the right and skewed to the left, students always get this backwards. Let's talk about this here. This is called skewed to the right. Most people, when I would ask them the question, is it skewed left or skewed right, they'd always say skewed left. No, it's where it's tailing off. That is where you say skewed right. It's tailing off to the right. All right. In other words, you have most of the data that are between 0 and 10 here, and you have these unusually larger values here. These are, you might call them outliers or very large values, but they are larger values. And so the data set here tends to be smaller values mostly, and then it tails to the right with the larger values. This means skewed to the right. Make sure you get this correct in your mind. The final exam typically has questions about this, and I've seen so many students get zeros on this test. It's such an easy question, and they get zeros and fail the test. They just fail it because of something like this. It's ridiculous. It's such an easy question to get right if you know what to look for, because it just means that the outliers are large. That's all. These are the outliers here. That would be skewed to the right. The opposite would be skewed to the left. Let me see if I have an example of that. Boy, they don't really give too many examples, but I guess I'd have to show you an example. Oh, I have an example skewed to the left. I will show you that in a few minutes. All right. The skewed to the left means that it tails off to the left. Most of the data is larger values, and there's a few outliers that are smaller. So it tails to the left. And again, I will show you an example of that in a few minutes. Just know that this is skewed to the right, and the one I will show to you will be skewed to the left. And then the symmetric one would be something that looks like that, or this. This is an example of symmetric. All right. That's where you draw a vertical line down the middle, and the left side sort of looks like the right side. It doesn't, it's typically not perfect, but it certainly looks pretty symmetric. That definitely doesn't look symmetric. All right. Now, let's get to this next section here. There is another way of looking at your data called the 5-number summary. This has, now we're not dealing with the average anymore, we're dealing with the median, all right? Remember, the median is that number in the middle. The definition of the median, by the way, is that 50% of the data is less than that number, and 50% of the data is bigger than that number. That's the definition of the median. Okay? So a 5-number summary, at least with this textbook, what they do is they create a box where the number up here is going to be your median. Down here, we have the lowest number in your data set. The smallest number goes over here to the bottom left here is your lowest number, and the largest number goes over here. Now the question is, what are these two numbers? Where it says lower quartile and upper quartile. What do they mean? Well, if you take your median and you divide, what the median does is divide your data set into two equal pieces. There's the lower half and the upper half. You can picture that, right? Lower half, upper half. If you took your lower half and found the median of all the numbers in the lower half, that number would be called the lower quartile. All right? What it means is 25% of your numbers in the data set are lower than the lower quartile, and 75% of the numbers are larger than that. If you took your median and divided the data set into the lowest half and the upper and the highest half, and if you took the highest half of the data and found the median of that half, that would be called the upper quartile. And 75% of the data is less than the upper quartile. 25% is greater than the upper quartile. So the point of doing this is that what the 5-number summary does, it divides the data set into 4 quarters. We have the lower quarter, which is lower than the lower quartile. We have the between the lower quartile and the median is the next 25%. Between the median and the upper quartile is the next 25%. And then between the upper quartile and the highest number in the data set is the highest 25%. You're basically dividing your data set into 4 pieces. All right. All right. Any questions about that? So when you calculate your lower quartile, you put it in here, in this spot here in the box, and the upper quartile is put in this spot in the box. I'm not going to do this particular one here. This is a confusing one. I'm going to leave this example of the 5-number summary to the example. Well, here's a good example here. Let's look at this one. This one here with the dollars and all is very confusing. Let's look at this one. This is simpler. It says here, how much do statistics students sleep? 190 statistics students asked how many hours they slept the night before. So they all 190 students gave an answer. And then, so you have 190 data points in your data set. And then you found the median. Now, can somebody look at this box here and tell me what the median is in terms of the number of hours of sleep?
Is it 7?
7, that's correct. What is the smallest number of hours that somebody said they slept?
3.
And what is the largest number of hours?
16.
Great, great. What is the lower quartile?
The lower quartile, is it the 6?
That's right. And what's the upper quartile?
The 8?
8, yeah. Good. So you read these correctly. All right. The median is 7. That's the number on the top here. The 6 represents the lower quartile. The 8 represents the upper quartile. The 3 represents the smallest number in the data set, and the 16 represents the largest number in the data set. This is the 5-number summary. Now, you can create what's called a box plot, which is a visual display of the 5-number summary. All right. So how do you do it? Well, you draw a horizontal line. It says over a vertical line, but for your test, for anything I give you, it's going to be horizontal. All right. Label it with values from the lowest to the highest. All right. So you're going to just draw a number line, lowest to highest, numbers in between 2. Then it says to draw a rectangle or box where the left end of the box is going to be your lower quartile and the upper end of the box will be the upper quartile. Again, I'll show you what way it looks. And then the median is going to be a vertical line in the box. Again, I'll show you what it is. All right, so actually, let's take a look at this. Here's an example right here. So what I mean is, here's your box right here. The left end of the box here is your lower quartile, 6. The right end of the box here is your upper quartile, 8. The median happens to be 7, but could it be anywhere? It could be anywhere inside the box. In this case, it happens to be 7. So you draw a vertical line at 7. The vertical line represents the median. And then outside here, you see these horizontal lines. Sometimes they call these whiskers. Sometimes people call this a box and whisker chart or plot. To the left here, it goes from the lower quartile all the way down to the smallest number in the data set, 3. And then they have a horizontal line that goes out to here, and then they have these 2 asterisks. I'll tell you what those mean in a minute. All right. But the asterisk all the way to the right happens to be the largest number in the data set, and they have one at 12, and then the next number number that's smaller than 12 happens to be 11, and then they have the whisker going all the way out from the 3rd quartile to 11. This will be explained in a minute. right, what we mean by all that. Now, once you draw all this, now, first of all, you don't know about drawing these asterisks until you do this little calculation in the middle here. So this is where you do need to know how to calculate, all right? But these are not, this is not calculus, this is simple arithmetic, all right? So don't be scared of what you're seeing. And again, this is open book, so you'll have access to how to do this. This is a particular slide you may want to keep near your side whenever you do this. Now, they have a thing here called IQR. You see this IQR here on step 4, and let's see if they describe it here. Go back. IQR is another name for that is interquartile range. Remember we mentioned that before. Interquartile range. It is the distance between the quartiles. Let's go back to this here, the 5-number summary. Now the range is 16 minus 3, 13. Everybody agree with that? This is the largest number minus the smallest number in the box here. Largest number 16, smallest number is 3. We subtract those two numbers, we get 13. That's the range. If we subtract the two numbers in the middle, this is the upper quartile. If we subtract if we take the upper quartile and subtract the lower quartile, 8 minus 6 is 2. That is called the interquartile range, IQR. That's just the letters for interquartile range. Everybody understand it now? If you subtract the two numbers in the middle, that is the interquartile range. And then if you subtract the numbers at the bottom, that is the range. Okay, interquartile range. Now, that's step 4. That's what they want you to do after you draw your box, is do this calculation here. And then step 5, they want you to multiply the interquartile range by 1.5. Now, in this case here, the interquartile range is 2, right? 8 minus 6. You multiply that by 1.5, you get 3. So 1.5 times IQR in this case is 3. Now, this is where you need to sort of take some notes or listen carefully. It says here that an outlier is any value more than this distance from the closest quartile. Geez, what the heck does that mean, right? You're looking at it and your head is spinning. What does that mean? Well, this is what it means. We've calculated 1.5 IQR is 3, right? It's 2 times 1.5. Now, what we want to do is take our upper quartile and add 3 to that number. What is the upper quartile? It's 8, right? 8. So we add 3, this number here, to 8, we get 11. Any numbers in your data set that are bigger than 11 is an outlier. All right? And that's why they have 12, which is in your data set, and they have 16, which is in your data set, have asterisks next to by them, because they are outliers. They are more than 1.5 IQR away from the upper quartile. It's sort of, I hope this makes sort of sense. What they're trying to determine is, are these data points so far away from this box that they would be considered unusual, unusually large? And the way they're doing it is they're calculating how wide the box is, which is the IQR. That's how wide this box is. They're multiplying that by 1.5, and they're saying any numbers that are more than 1.5 IQR away from the right part end of the box, or the upper quartile, is going to be an outlier. Any number that's bigger than 11 is an outlier. Now, you do the same thing on the left here. We'll look at small outliers. What you do is you take your 1.5 IQR, which is 3, and subtract it from the lower quartile. So this time you're subtracting it. Why? Because now you're looking to the left. So when you subtract, now the lower quartile is 6. When you subtract 3 from that, which is 1.5 IQR, you get 3. Any numbers that are lower or smaller than 3 will be considered a small outlier, an outlier on the left. Well, it happens to be that the smallest number in your data set happens to be 3. 3 is not smaller than 3, therefore the 3 is not an outlier. If we had, let's say, 2 or 1 in the data set, if somebody said I only slept 2 hours, that would be an outlier. But there's no outliers. So in this case, there are no outliers that are small. So therefore, when we draw this box plot, we're going to draw a horizontal line that goes from the lower quartile all the way down to the smallest value, 3. And none of these values in between here are outliers. On the right hand here, we have 2 outliers at 12 and 16. And then what we do is we draw the horizontal line all the way out to the next number, which is just below these 2 outliers, which happens to be 11. And then we have the outliers at 12 and 16. Okay. So this is called a box plot because it gives you the 5-number summary, the minimum, the lower quartile, the median, the upper quartile, and the maximum, which just happens to be all the way out here. Now, if in this case there were no outliers, then you would simply draw the horizontal line all the way out to the maximum value. But these 2 numbers here are outliers. According to this calculation, they're both bigger than 11, and therefore we put an asterisk next to those numbers. All right?
Is it always going to be 1.5?
Yes. 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 So always, once you calculate your IQR, interquartile range, you multiply that by 1.5, and then you add that to the upper quartile to see if there are any large outliers, and you subtract it from the lower quartile to see if there are any small outliers. That's basically it. If you get this straight in your head, this is not a hard thing to do. You just have to sort of.
It is hard. It's hard. I don't even understand none of it.
Well, you need to look at the example I'll be doing in a minute. The example will reinforce it. All right. But just follow the steps. That's all it is. Follow the steps. Okay. You know what this reminds me of? I do taxes. And before, when they had the tax software, you'd have to read the tax guidelines of how to do something. And it would read just like this. You know, when you fill out a tax form, it would say, all right, compute this. This is the formula. This minus this and this. And you put this in this particular part of your tax return. And then you multiply it by 3 and you put it somewhere else. And it's the same thing. It's just following steps and doing exactly what the steps are telling you to do. That's all. And you just have to follow it. And if it seems confusing at first, it's because you're trying to understand this all at once. Just understand it step by step, and then it'll become clear to you. All right. Interpreting box plots. Now, here is the deal. 25% of the data will always be between the lowest value and the lower quartile. 25% of the data will always be from the lower quartile to the median, this distance. 25% of the data is going to be from the median to the upper quartile. And 25% of the data is going to be from the upper quartile all the way to the maximum value. Now you notice these distance, even though I'm saying these are 25%, these 4 25%, they all have different distances, right? Some of them are longer, some of them are shorter. What does that mean? That means that if the 25% distance is shorter, it means the data is more crammed together. Doesn't that make sense? It's more crammed together than if the 25% is more spread out. So between Q1, and not Q1, between the lower quartile and the median is 25% of the data. That distance is what? It's from 6 to 7. It's only a distance of 1. 7 minus 6 is 1. But from 3 all the way up to 6 is 25% of the data. So that means the data from 3 to 6 is more spread out than it is from 6 to 7, or crammed together. That the idea? So you can tell how spread out the data is when you do that. So 50% of the data goes from what? From 3 up to 7. From the smallest to the median is 50%, and from 7 all the way up to 16 is also 50%, from the median to the larger value. Where is it more spread out? Is it from the lower end or upper end? When you're looking at this chart, is it more spread out? Is the lower half more spread out or the upper half more spread out?
Upper.
Upper, yeah, because it's a longer distance, right? If 50% of the day goes from 7 to 16, which is a difference of 9, and the lower half goes from 7 to 3, which is a distance of 4, the data, the lower 50% is more, the data is more condensed, it's more squeezed together than it is from the upper half. This gives you the idea that this is probably right skewed. It's tailing off to the right, all right? More of the data is on the lower end, less of the data is on the upper end, right? And I think we showed that with the histogram before with this data set, right? The histogram before, we saw the histogram. See if we can find it again. Okay, is this the same one? No, it's not the same one. No, they don't have it here, but a histogram would look like something like this. That's my point. It would be tailing off to the right. Okay, but you could also see it with a box plot if you wanted to look at that. All right. You could also make the following statements. You could say a quarter of the students slept between 3 and 6 hours. A quarter of the students slept between 6 and 7 hours. A quarter of the students slept between 7 and 8 hours. And a quarter of the students slept between 8 and 16 hours. You could also say half the students slept between 3 and 7 hours. You could also say that half the students slept between 6 and 8 hours. This is called the middle 50%. The IQR tells you the length of the middle 50%. This is the middle 50%. So you could say 50% slept between 6 and 8 hours. 50% slept between 7 and 16 hours. You could also say 75% of the students slept between 6 and 16 hours, 75%. How do I know it's 75%? From 6 to 7 is 25%, another 25% from 7 to 8, and another 25% between 8 and 16. So between 6 and 16 hours, 75% of the students. And also between 3 and 8 hours is 75%. How do I know? Because from 3 to 6 is 25%, from 6 to 7 is 25%, and from 7 to 8 is 25%. So therefore, from 3 to 8 is 75%. Typically ask questions like that on tests, right? Just, you have to understand that it's broken up into 4 quarters. Sometimes you'll look at comparative box plots. In other words, you're looking at the same data, the same numerical variable with 2 groups. What's the fastest you have ever driven a car? And they ask you in miles per hour. Well, for male students, there were 87 of these male students. Tell me for the male students, what is the median in terms of the fastest they ever drove for male students? What's the median?
110.
110 miles per hour. What's the median for females? 100 out of the 102 females in the study.
89.
89. Okay. What's the fastest any male said they drove?
150.
Female.
130.
Right. What's the slowest that a person said they drove? Not the slowest, but what's the slowest, fastest
30,
number?
30,
That's for females. For males,
55.
that's right. Good. And then we have the lower quartile, upper quartile for each one of these boxes. Okay. Now, if I ask you a question like this, now also I wanted you to know, I wanted to ask, how many outliers are there for males?
1.
One. Is it lower or upper?
Lower.
How many are there for females?
4.
4. Okay, good. Here's a question for you. It's a yes/no question. Is the upper quartile equal to, for the females, equal to the lower quartile for males? Or does it seem that way? Is the upper quartile for females the same as the lower quartile for males? Are they equal to each other?
Yes.
Yes. 95, right? And you can see it on the chart here. The upper quartile is at 95 for males, and the lower quartile for females, and the lower quartile is the same for males. And you can see it in the 5 number summaries. Here's the lower quartile 95, here's the upper quartile 95. See, they match. Okay. Now tell me, from what you see here for males, does it look like symmetric or left skewed, right skewed for males? Does it look left skewed or right skewed for males? Or symmetric? What would you guess?
Right skewed?
All right, why?
I don't know. I'm looking at.
Think about where the median is and look at the 2 endpoints, the lowest and largest. If it's about symmetric, the distance from the median to the lowest and upper should be the same. Now you're saying it's not, that's fine. But you're saying it's right skewed. Why would it be right skewed? Remember, skewness, it's tailing off. Tailing off.
I was looking at the higher numbers to the right. I don't know.
You don't look at the higher, you have to look at the whole thing. Whole thing. The median is 110 for males. The distance from the median to you can see it from in the box here. From 110 to 150 is 40 distance. And from the distance from the median to the lowest value is 55. So which distance is larger? Is it from the median to the lowest or the median to the highest? Which distance is larger? Just subtract numbers. This is 40, this is 55. Which is bigger? You see what I'm doing? I'm just subtracting these numbers. I'm looking at the distance from the median to the lowest, median to the highest. The median to the highest, the lowest is 55. 110 minus 55 is 55. The distance from the median to the largest is 150 minus 110, which is 40. Which is bigger? Which distance is bigger? You can even see it here. It's this distance. It's from the median to the smallest. If 50% of the data is over a longer distance, it means it's more spread out. Do you get that idea? 50% of the data to the left, 50% of the data to the right, and yet it's more spread out on the left because it's a bigger distance. That means it's tailing off to the left. That's left skewed. Upper one is left skewed, not right skewed, left skewed, because it's spreading out, it's more spread out, the data. Let's look at the bottom for females. Okay. Distance between the median to the upper and the median to the lower. Which one is more spread out? You can even visually see it. From the median, this is the median, to the upper, median to the lower. Which is the bigger distance? Left or right?
Left.
Yes. And that means tailing off to the left too. So these are both left skewed. Okay. What does that mean? It means there's some unusually small, for the most part, some unusually small. Now, it happens also that we have a couple outliers on the right here too. So this is a little more complicated, the one for females, right? And the reason why this are outliers is because the distance, the interquartile range is so small here. You see the interquartile range? It's not very large, it's only 15. Well, it's 35, the interquartile range is 35 for males, so it's small. And that's probably why these are outliers, all right? Because of this interquartile range being so small. But this is definitely, in my view, this is more skewed left than all right. And then I would say the following: what percentage of the females are between 50? All right, let me rephrase this. Between I'm going to change my mind on this. What percentage of females are between 30 and 80?
25%.
25%. What percentage of the females are between 80 and 130?
75%.
That's right. Good. What percentage of the males are between 55 and 110?
50%.
That's right. What percentage of the males are between 95 and 120?
50.
50%. It's the middle 50%. Right. Right. So you just have to think about the quarters, right? Where does the quarter start? You know, they start from here. That first quarter goes from the asterisk out to the lower quartile. The next quarter is from the lower quartile to the median. Then the next quarter is from the median to the upper quartile, and then from the upper quartile to the maximum. Same thing down here. From the smallest value to the lower quartile is 50%. 50% from the lower quartile to the median, 50%, excuse me, 25% from the smallest to the lower quartile, 25% from the lower quartile to the median, 25% from the median to the upper quartile, 25% from the upper quartile to the maximum. Okay. All right. And I'll just tell you a couple more things, then I'll show you this example. And might have to continue with the example at the beginning of next session. I want to take this slow enough so that you can understand it. The traditional measures are called the mean, variance, and standard deviation. All right, so these are the additional ones. The mean, of course, is the average, representing the center, just like the median does. The standard deviation represents the spread or variability in the values, and the variance, this is important to know, is the square of the standard deviation. All right. Typically, we use the mean and standard deviation if the data set is somewhat symmetric and there are no outliers, but to be honest with you, in real life, nobody does this. Everybody uses the mean and standard deviation for all data sets, but they shouldn't. They should use the median and the interquartile range if the data set is skewed left or right. All right. All right, and then they give some examples here of why we wouldn't necessarily want to use the mean. For example, if we have 4 classes and the class sizes were 20, 25, 35, and 200, and we want to take the mean is going to be what? It's going to be 70. When we add those 4 numbers up, does 70 seem to represent any of these numbers in the data set? That's because this 200 is unusually large compared to the other 3. So they're making the point here is that the 200 is distorting the average, making the average larger. The 70 doesn't really represent those 4 classes very well, the average class size. So it's better to go with the median. In this case, the median would be the average of these 2 middle values, which is 30. And that represents the data set better. All right. So their point is that if it's really, really skewed, the mean is just not a very good measure of the center of the data set. The median would be a better measure. Now, standard deviation. Standard deviation measures the average. It's roughly the average distance of each value from the mean. Okay. If there's no spread at all in the data set, and notice all the numbers are the same, the standard deviation is 0. That's the smallest number of variability. So in the final exam, I'm going to tell you this up front. I typically ask a question like, about the nature of the standard deviation or variance, and I basically say something like, it can be negative. Well, it can never be negative. It can never be a negative number. Variability is 0 or above. 0 meaning no variability, and if there is some variability, some differences in the numbers in the data set, then the standard deviation will be greater than 0. It'll never be less than 0, right? Now, how do you calculate the standard deviation? It's a complicated calculation, but it's not something that I'm going to necessarily ask you to do, but it's something that your calculator, if you have the TI-30X calculator, the scientific calculator from Texas Instruments, there is a little bit of a stat feature in here where you can enter data, and it'll actually calculate the standard deviation for you. I'll show you that feature next time, because I think we're running out of time. But how do you calculate standard deviation? You calculate the mean or average first, and then for each number in the data set, you take the mean and subtract it from that value, and it's called the deviation from the mean. Then the third step is to square each of those deviations from the mean, and the fourth step is to add up all those square deviations. All right, once you had it added up, that'll be the numerator of what we're going to be calculating. In the denominator, we're going to just calculate the number of values minus 1. So if there's 20 numbers in your data set, the denominator is 20 minus 1, which is 19. So the sum of the square deviations, this is step 4, divided by the number of numbers in your data set minus 1, gives you what's called the variance. And then you take the square root of that number, and that's called the standard deviation. And that's why the variance is the square of the standard deviation, because to get the standard deviation, you take the square root of the variance. All right? And the reason why, and just to be just very brief about it, why, you might ask, why do you have to take the square root of variance? Why don't we just use the variance? And the reason is because when we square these deviations, we're literally squaring the units of measurement, whether they're measured in inches or pounds, whatever the units of measurement are. We're squaring the units of measurement. Therefore, the last step 6 is what we have to take the square root of the variance so that we can get back to the original units of measurement. All right, and then they give an example here, how to do all these calculations, and they've eventually come up with the standard deviation being 10. And then they have a little thing about is average, normal, and all of that, which I don't think is very much something we'll look at. But anyway, here are the formulas if you want to look at them. If you were taking a regular stat course, you'd have to know all these symbols, what they mean. The X with a bar above it is the mean. And this symbol here with this Greek symbol, it's called sigma, means you add up all the X's, all the values in the data set, and you divide by n, the number of numbers in the data set. The variance, they typically say S squared. Here's the formula for that. That's what we were doing on all the steps. And then well, you can ignore that. That's for computation. And then the bottom says, just take the square root of the variance and you get your standard deviation. But if you just follow the steps that were just given, you'll be able to calculate the standard deviation. Now, one thing we're going to do next time, and I guess we'll cover this beginning of next section and then do chapter 8, is I want to do an example of all of this. And it's at the bottom, it's at the end of your textbook. So I'm just going to share to you very quickly what it will be. So chapter 7 problems, it's basically problems. If you look at the end of the textbook, and if you have the ebook, by the way, it's at the end of the chapter. You'll see at the ebook will be all these exercises, but it'll be 4, 5, 6, and 7. All right, they all refer to the same data set that we're looking at before. All right, and I show you how I created the stem plots. That'll be the first thing. And then I show you a way of creating a histogram. And this histogram will prove to you that this data set is skewed to the left. That was the point of doing the histogram, to show you that. And then I show you how to find the median, and then the mean, standard deviation. They're just coming in right now. It's kind of late. And then quartiles. I'll show you how to find those. And then the box. Here's your box with the 5-number summary. And there's your box plot. And then I do the calculation down here of how to find where the outliers are. Okay. So all of this will be done in the first 15 minutes of next session, and then we go right into chapter 8. We'll post this to you. Not now. I'll post it to you after I've reviewed it on Thursday. All right, and then I'll post it and then you can take a look at it. All right, but this is a basic, these problems here are a review of everything we did today. And you just need to study this, make sure you understand how this is done and how to interpret it, and then you'll be good to go for chapter 7. Any questions?
How long is it before the next quiz? Because I don't get this.
The quiz will be next week.
I'm really discouraged.
The quiz will not be any calculation, just the vocabulary. Calculations are left off the quiz. The calculations will show up on test number 2. Don't be discouraged, because many times you won't get it the first time, but you will eventually get it. You just have to work through the problems.
I'm just not
with your
good at math. That's what it is. I don't comprehend numbers.
Well, that means you just have to review it a few times. That's all. But anyway, guys, I'll see you next time. I'll stop the recording. Any other questions? And just don't worry. All right. That's why I'm doing these review problems also, that you will get a chance to review it and understand it.
So what definitions are going to be on the quiz? Because we did a lot of calculation today.
Well, there's also chapter 8 too.
Oh, all right.
We haven't done that yet.
Okay.
All right. All right. I'll see you next time. Okay.
Okay.